Hey, my name is Alex, and today I'll present to you our paper called Variational Predictive Routing with Nested Subjective Timescales. This is a joint work with Qinghai and Zafeirios Fountas from Huawei Research and Development. One of the key benefits of hierarchical generative models is the increasing level of abstraction they can acquire in the deeper levels. For temporal datasets and models, this abstraction can translate to a temporal one, where slower and more static features could be represented in the higher levels of the model. In most such models, temporal transitioning is often realized either at every time step or over fixed intervals. However, such rigid structure of belief updates may not be optimal for learning the disentangled temporal features across the model's latent hierarchy, and thus lead to poor properties of temporal abstraction. These approaches also seem to be less compatible with the insights from neuroscience, where evidence suggests that the brain dynamically employs its hierarchy to segment continuous streams of observations, with timescales ranging from milliseconds to minutes. So can we create a model that can discover and learn the underlying spatiotemporal hierarchy of a dataset? Take this one, for example, where a ball bounces around in a box while changing its color upon every bounce. You can see that the position changes at every time step, while the color changes every few time steps. A hierarchical generative model that could learn to represent these two temporal features across two different latent levels is what we would expect in a model that addresses this challenge. This property would also lead to the model's ability to segment sequences of data optimally. And thus we come to VPR, an event-based hierarchical generative model that organizes latent representations of video features in a temporal hierarchy based on their rates of change. VPR consists of latent blocks stacked together in a hierarchy, with each block consisting of three deterministic variables, C, D, and X. These mediate the three ways of communication between other blocks: temporal, bottom-up, and top-down. These deterministic variables are used to parameterize a random variable S, which is the model's belief state at level n. Stacking the blocks together creates a VPR model. VPR's unique properties are most evident when we look at an unrolled version of it, here for example 5/5 time steps. First, at any level and time step, VPR can decide to block the ongoing bottom-up encoding, thus stopping the higher states from updating. This in turn implies that the top-down context received from the levels above will remain constant. Lastly, this also implies that the transitions or updates in the different levels of the model occur over different and flexible timescales, where updates become increasingly rarer the higher you go up. This is what we call subjective and nested timescales in the paper. But when does VPR actually stop the propagation of bottom-up information? Well, VPR will initiate an update on a block state only if it could detect a change in the features represented at that particular level. If no such change is detected, the encoding is blocked from going further up, thus enforcing a strict feature-centric hierarchy of timescales. Occurring at every level of the model, this event detection mechanism is designed to capture both predictable and unpredictable changes in the observable features, and is non-parametric, thus not requiring for a separate parameterized model. This mechanism ultimately results in the model's ability to distribute its temporal representations across its hierarchy, reduce computational redundancies, produce jumpy predictions from one event to another, and more. We use a variety of datasets, two of which are shown here, that consist of basic features that can be disentangled based on their temporal properties. We show that VPR is able to disentangle these temporal factors of variation. For example, producing a rollout using level 1 while keeping level 2 fixed. In this case, we can see that VPR predicts positional changes of the ball while its color stays fixed. And vice versa for level 2, VPR predicts color changes while the ball's position stays the same. We show the same property in the 3D shapes dataset, as can be seen here, where the temporal factors of variation seem to be disentangled across the model's latent hierarchy, allowing it to produce accurate, feature-specific, and jumpy rollouts. We also validate the performance of VPR's event detection mechanism, showing that the model is able to partition the provided sequences into optimal segments. This performance also holds even if we speed up the dynamics of the dataset, as the model adjusts its rates of update while reaching the same accuracy of event detection. We similarly demonstrate that the subjective timescale rollouts produced by the model are accurate at predicting future events over very long intervals of time, as each prediction time step represents a jump in the physical timescale of a ground truth sequence. Thank you very much, and please make sure to visit our website.